All right, so after our discussion on what a basis is, we've really built up to that in the previous sections, talking about spanning sets of vectors that will span a vector space, so you really want to understand what that means, as well as the concept of when a set of vectors is linearly independent. So if we put those two things together, we get what we call a basis, right? If a set of vectors from a vector space are linearly independent and span the space, then they must form a basis for that vector space. Okay, with that, we're now able to talk about the important concept of dimension, which is kind of intuitive in a way. Some of you will understand this makes sense, I think, in the vector spaces that we're familiar with. But let's take a look at this first. And this theorem we're going to start with is that all bases for a finite dimensional vector space have the same number of vectors. So if you go back to our friendly neighborhood vector space, namely 3 space, when we think of 3 space, what's a basis for 3 space? Okay, so I hope that you will automatically jump out and say, well, hey, I know a basis for 3 space. It's I, J, and K. Right, the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right, those are 3 vectors in 3 space. They are linearly independent and they span all of 3 space. But there are other bases for 3 space. In previous lectures, we proved that a given set of vectors was a basis for 3 space. And if you go back to that example, you will see that there are 3 vectors in that set. And in fact, this theorem right here will say that any basis for 3 space must have 3 vectors, because it says any basis for a finite dimensional vector space has the same number of vectors. Okay. Now the proof of this theorem I'm not going to prove, but it makes use of the following, and that is that if we have a finite dimensional vector space that has n vectors in the basis, okay, it has n vectors in the basis, then if we have a set of vectors in that same vector space with more than n vectors, more than the vectors that we have in any basis for that vector space, then that set of vectors must be linearly dependent. Okay, linearly dependent. And we can think of this again in context of a friendly neighborhood vector space like 2 space. Okay, if I think of the vector space 2 space. Now we know a basis for 2 space is just I and j, right? The vectors, so if we want to think about it, the vectors 1, 0 and 0, 1, right? Which some of you call I and j. These are 2 vectors that span all of 2 space, and they are linearly independent, right? Because they span all of 2 space, right? If I throw another vector into this set, so let's do this. Let's throw in the vector 1, 1, right? Well, obviously 1, 1 can be written as a linear combination of the first 2, right? In other words, if I take this vector plus this vector, I get this one. So obviously this set is now what? Linearly dependent, right? Now, these vectors actually still span all of 3 space, right? But they are clearly linearly dependent. And that has to be the case, right? Because we know from this case that if we start with these 2 vectors and add any other vector, then since these 2 vectors span all of 2 space, any vector we add has to be able to be written as a linear combination of those 2. Okay, but another way we could look at it from is this. What if I look at the vector 1, 0, 2, 0, and 3, 0? Right. Well, those 3 vectors, do they span all of 3 space? Well, no, right? Clearly not, because they all have 0 in the second component. So I could not get, for instance, the vector 0, 1 by taking any linear combination of these 3. Okay? But we know any basis for 2 space, right, is going to have to only include 2 vectors, and we have 3 vectors here. Okay, what do we definitely know if we have more? This is saying that what the set must be linearly dependent. And again, you can see how this set is linearly dependent. Clearly, this vector here can be written as a linear combination of the first one because it's just a scalar multiple of the first one, right? 2 times the first one gives me the second one. Same thing with the third one. 3 times the first vector gives me the third vector. So the point is that if we have a basis for a vector space with n vectors, if I have more than one vector, more than n vectors in the set, then the set must be linearly dependent. We really can't assume anything about whether the set spans or does not span the vector space, because in this case, this set of 3 vectors, linearly dependent in 2 space, they span all of 2 space, right? Because we've got this vector and this vector. I threw this one in as well. These span all 3 space, but this set, right, of 3 vectors does not span all of 2 space, rather, all of 2 space. But both of these sets are linearly dependent, and that's what this thing is saying. Now, if we have fewer than n vectors in the set, then that set does not span V. Think about it. You know, if we're spanning 2 space, what do we need? We need at least 2 vectors. One vector cannot span all of 2 space. One vector, what will it span? It will span a line, right? If I have one non-zero vector, any scalar multiple of that vector will simply be a line passing through the origin. For example, so again, thinking of our familiar 2 space, for instance, to illustrate this. So you have got to get these 2 facts down. These are imperative that you understand these 2 facts, and we're going to test you on those here in a moment. So again, if you have n vectors in any basis, then if we have more than those n vectors, the set is linearly dependent. If we have fewer than those n vectors, then the set does not span V. Okay, so all this is involved in the proof of the above, which is that any finite dimensional vector space has the same number of vectors in any basis for that space. And that allows us now to define dimension. Dimension of any finite dimensional vector space, denoted DIM, and then in parentheses we put the vector space symbol, whatever the vector space is, V. It's defined to be simply this, the number of vectors in any basis for that vector space. The number of vectors in any basis. So finding dimension is easy once you have a basis, right? Because once you have a basis, you just count up the vectors. How many are there? That's the dimension. Now, and the reason we can define that clearly is because of this theorem. Any basis has the same number of vectors for a given vector space. Any basis for a given vector space has the same number of vectors. And that number of vectors is called the dimension. So going back here, now we can say if a finite dimensional vector space has dimension n, if we have more than the dimension vectors, more than n vectors, then that set is linearly dependent. If we have fewer than the dimension vectors, then that set of vectors cannot span the vector space. Okay, let's talk about dimension of some vector spaces. First of all, the dimension of the zero vector space. Remember, the zero vector space is simply the vector space containing only the zero vector. It's the trivial vector space, if you want to call it that, but it's the zero vector space. That dimension has to be defined to be 0. That means that any basis for this vector space cannot have any vectors in it, or what we say, it's the empty set. You say, well, that doesn't make any sense. Well, let's think about this. What would a basis be for the zero vector space? What vector would have to be in it? Well, someone says the only vector in the vector space is the zero vector. So why can't this be the basis? Well, if you remember when we talked about linear independence, what happens if you throw the zero vector into a set of vectors? What does that cause the vectors to be? That causes the vectors to be linearly dependent. In fact, if you have if you have a set with one vector, that set is linearly independent if and only if the vector is non-zero. It's linearly independent if and only if the vector is non-zero. Therefore, if it's the zero vector, It's linearly dependent. And a basis has to be what? Linearly independent. So I can't put the 0 vector in there. So again, the empty set is the basis for the 0 vector space. So its dimension is defined to be 0 because of that. What's the dimension of one space? Well, one space is just the set of real numbers. What's a basis for the set of real numbers? A basis for the set of real numbers is really any non-zero real number. The easiest one to think about is the number 1, right? Every real number can be written as a linear combination of the number 1. And in this case, a linear combination is just what? Any real number scalar multiple, right? So 4 is 4 times 1. 2/3 is 2/3 times 1. The square root of 7 is the square root of 7 times 1. In other words, every real number is a multiple of 1. And 1 is not 0, therefore that is linearly independent. So real set of real numbers has a basis always containing 1, and therefore its dimension is 1. It contains one vector, in this case vector. What about ordered pairs, right? A set of all vectors in 2 space. What's the dimension of 2 space? Well, what's a basis for 2 space? We just talked about it right up here, right? Right here. IJ, right? 1, 0, 0, 1. Every basis for 2 space has how many vectors? 2. So the dimension of 2 space is 2. What's the dimension of 3 space? The basis for 3 space has how many vectors in it? Think of the basis we know, I, J, and K. 3. This is real tough, right? Do you get the picture here? What's the dimension of n space? N. Right? Makes sense. Right? We talk about 2 spaces being what? 2-dimensional. We talk about 3 spaces being what? 3-dimensional. Right? It makes sense. What about M22? What's the dimension of M22? Do you remember a basis for M22 in our previous videos? You remember a basis for M22? How many vectors did it have? Go back and watch the video if you haven't. The basis we had 4 vectors in it. 4 vectors in it. The vectors being 2x2 matrices, right? And they were, the matrices were, I had a 1 in one of the entries and zeros everywhere else. And there was 4 different matrices of that size, right? Those 4 matrices span all of M22 and they're linearly independent. So the dimension is 4. So what are we getting the 4 from though? It's basically from the fact that every 2x2 matrix, right, has what? 4 entries. And each of those entries can be distinct. Therefore, the dimension is 4. Well, with that reasoning, what's the dimension of M34? How many entries in a 3x4 matrix? 12. 3 times 4 is 12, right? So in general, what's the dimension of MN, the set of all m by n matrices? Simply m times n. What's the dimension of P sub 2? What is P sub 2? It's the set of all polynomials of degree 2 or less. Do you remember what a basis was for this? Go back and look at the video on basis. We talked about it. Here's a basis for P sub 2, the set of all polynomials of degree 2 or less. The basis is 1 x squared. These are the 3 polynomials, these are 3 polynomials that form a basis. Clearly they're linearly independent, right? I cannot write 1 as a linear combination of x and x squared. I cannot write x as a linear combination of 1 and x squared, and I cannot write x squared as a linear combination of 1 and x. That is clear. And so they're linearly independent, and they span all the space, right? Every degree polynomial of 2 or less can be written as a linear combination of these 3 polynomials, right? So what's the dimension of P sub 2? Let's count it out. 1, 2, 3, right? Basically, we think about it what? As all the powers of x, right? Degree 2 is what? X squared, and then what? The constant term. Don't forget the constant term. So if it's P sub 3, what's it going to be? X squared, x cubed terms, and then what? The constant term. So the dimension of P sub 3 is 4. So what's the dimension of P sub n based on this? You say n plus 1, give yourself a cookie. That's good. So these are all the familiar vector spaces, and we need to know the dimension of those vector spaces. Just to make sure you truly understand what we're talking about here, if S equals this set of 4 vectors is a basis for the vector space V, then what is the dimension of V? I hope you're saying 4. If you didn't say 4, then you don't understand what we were talking about. You might need to rewatch this video.